like this. Thank you. Okay. Okay. Hi, everyone. I'm a PhD student, first year, and I'm working in real-time system and scheduling. I'm studying for in this topic, and my first work here is to. Okay. My first work here is to verify some temporal constraints. So this part is going to be mostly theoretical at first because I want to explain first what I did theoretically, and then whether this work was already done in the kernel or it was already implemented. Maybe I'm just late to the work already. So why did I do this? Because first of all, there are multiple scheduling classes, and we have sched deadline for already checking whether our runtime and deadline are already respected. But I would like to know if in other scheduling classes I can get any reasonable latency or CPU time guarantees. So I just want to check if there's an easy way to see how a task is progressing. So I'm going to go on the overview per task of the scheduling theory a little bit. So we have the task that is just a process ID number, and the sched switch event that I'm going to use, I'm going to conceptually define it as in and out, because when a task gets put on the CPU, for me, it's a sched in, and when preempted out, it's a sched out. I'm going to take those in to the K and out to the K as the timestamps of those events. And that will basically tell me how long the task has been on the CPU or not. So we have that the scheduling function 0, 1 is just if it's on the CPU or not in the CPU. So 0 is when it's off, 1 is when it's on. And the schedule with the integral is simply the sum of the execution of the all the executing periods. Therefore, it's this staircase function that constantly goes up. Now, my issue here is that I'm checking it against a function called SLBF, where it's the schedule lower bound function, and this is of a linear variety. Therefore, we have a certain latency that is annotated with delta, and a certain rate or bandwidth that I annotated with alpha. So in this example here, I put alpha 2/3 and delta at 4. But the difficult part of this this checking, of course, is not that the sum of the execution is always be low, because if it's like this, it's kind of trivial in that sense. But the issue is that since it's for every t0, this linear lower bound function can start at any point of the scheduling function. Therefore, at any point in time, I should check whether this condition is violated. Ergo, at every point. For example, here we have that if I take t0, 7, I have a violation of the condition. Therefore, this wouldn't happen with t0, but with t0, 7, I have this. Therefore, how do I check it? How do I actually check all of this? Of course, I know that check every single point that the scheduler function had is a little bit unfeasible, because it would mean saving every point. And that is not correct. So checking back this function here, we know that we can categorize these slopes as just which one is the highest. Therefore, by just saving which one is the highest and calculating the time before a collision happens, I can just save one single value. And if I can calculate it in some way and check this value is always under a threshold, or again, in my case, never negative, this condition is saved, it's fixed. Therefore, before in gray, we have the previous scheduling function. In blue, there's the highest lower bound latency. And in black here, we have my own metric going to basically build up. And therefore, we have that as soon as it becomes 0, we have the intersection in the lower bound latency. But of course, in the algorithm I checked, I have a small issue because I'm only going to find out at the next scheduling, when the task is next scheduled. So the algorithm that I figured out is straightforward, as we start from Slack with the latency maximum that we have possible. Ergo, when we set delta here, it's simply the time that I can wait before having to be scheduled on the CPU. And when I say in and out, and I do the subtraction, it's simply the amount of time that I spent out of the CPU when I update at sched-in, and at sched out, it's the time I spent in the CPU. Therefore, when I spend time in the CPU, I should have my Slack being higher again, because I get basically more time before I need to be rescheduled again. And the important thing that to me really changes the entire algorithm from just being a sum of the execution time is that this Slack out has a minimum with the latency at most. Therefore, this is when, if I have to re-update at the latency, that means that I'm basically taking a new highest SLBF, the lower latency bound. So apart from this is for me a way to make up a number value that I can basically check for how much time remaining I have before getting scheduled. Therefore, I report the example here. Again, it's easy to see that at the Slack out point, ergo, when I'm at out 1, I should have been much higher from the dotted line, but I get stopped because of the cap at latency delta. And that's what makes me able to just be updating the T0, because otherwise, if I didn't do this, the T0 would always start from 0, or that is the first point that I measure. How difficult is to do all this? And my implementation was simply check the sched switch event, put a trace point in there, and then just filter for my process ID that I'm attending, and then just update this Slack. Few things that I had. I did try with the runtime verification subsystem first. I'm simply augmenting the automata that it's here, that I use the .to kernel command to exactly make a prototype and then augment it with the timestamps. And I was just forcing an illegal transaction when the time was violated. This in timed automata terms, these transactions are only possible when the condition is true. As in, if the time that I was out is more than the Slack, then I can do only that transaction. Otherwise, I'm forced to just fail up there. I'm not sure how to point. Here. Otherwise, I'm just here in this cycle of updating my Slack with adding some time or removing some time. And of course, here I'm just resetting the counters because I'm basically counting how much time I was in or out of the schedule of the run queue.
No, just editing on the initial The current automata support is without having timing or
Yes,
without
it's
parameters,
without.
but it's totally okay to have the parameters inside the monitor because the
Yes.
monitor is isolated on itself. So you can just argument it as you want.
My full, actually my full, not thesis, but one of my goals is technically augment this with timed capabilities for events. And I would like to eventually augment the automata support, not just to change an automata, but also to have a timed logic, like transform a time logic into an automata and then having it already be done to this.
The reason I choose the deterministic automata is because all those things are possible.
Exactly. And my point is I wanted to extend this because as coming from academia, it's a bit difficult getting into the kernel internals. And some, even just an automated tool like the runtime verification, a lot seeing how a module is set up.
That was exactly the idea. And that's why the automata, because we can extend, it's the simplest type of automata because it can extend. So it's easy to generalize.
Exactly. And I made quickly another version of this as well, just to test myself in eBPF. This is just, again, trace point at the sched switch. I'm sending events through a ring buffer and therefore already filtered. And then I'm just processing with the new timestamps, still based on the same formula that I showed before. Again, I tried to change the alpha rate because I'm expressing it as a numerator divided by a new denominator. Because when I did the module, I know that I cannot do floating point divisions in the kernel. And therefore, I had to modify a little bit this formula of 1 minus alpha divided by alpha in order to, one, put the integer division at the very end, so I would lose as little as the precision. Basically, I'm losing an average the half of the numerator value. And practice, I saw that since the Slack value is actually, let's see, since the Slack value is usually tied from latency to 0, it's not a big deal if it's a little bit inaccurate. Because I'm never, as soon as I get back to the delta, the latency I have, it's going to be reset. So
just editing on top of this. This is using the .2 BPF, right?
Yes.
So there is an implementation of the same thing that I have in kernel using automata. There is an version in the BPF.
I did see it. I sadly was running out of time to use that one properly. So I just took the Bootstrap library, used the minimum use. I'm tracing this. I just want the value out as a mono. I just want to know the value in a more, I don't have to recompile the kernel every time.
Yeah. With the .2 BPF, it's not yet inside the kernel because I was missing a part that is checking if the libbpf library was available on the system. I could link it at compilation time so it doesn't break the compilation when Linux run it.
Okay.
Which is a problem that Steven and I know well when we break compilation in front of Linux. But now it's easy to bring the .2 BPF and to integrate this with the RV.
I can probably port this very easily.
Yeah. And then we can bring into the RV command line in tools, verification, RV, because now I can do the compilation with BPF. Okay. You can use it either in the kernel or on the BPF version on RV. It's all fine.
Exactly, whatever. Because thanks to the runtime verification subsystem that Daniel did, thanks to that, I can basically eventually make a reactor that when these conditions of the Slack less than 0 happens, I can make something happen eventually. What I was thinking is exactly, maybe I'm just raising the priority of the task. Maybe I'm changing the scheduling class of the task. Because if this is basically an automated way to see if the task is not getting enough bandwidth at this latency, then I need to do something about it. Some experiments. We have tried some deadline. I used a CPU set because with deadline I cannot set an affinity. And we had to run m+1 tasks over M core, and giving a runtime of m divided m+1 times the period, I can get basically m+1 tasks fitting into M cores, but one of the tasks is going to always having to switch cores, basically. And this is kind of the extreme edge case of seeing how multiple tasks interact with it. We have something interesting. One, I first ran it without running all the other M tasks. So I just ran one single task with that runtime and period. And I have this, since the Slack updates in and out, it's always going to be a kind of spike graph, I guess. And it's a lot more consistent with this, probably because I'm filling the CPU almost entirely. Therefore, there's very little time for the scheduler to move it even a little bit, basically. Because we had also some points where we don't utilize it full, but just a little bit less to get the admission test right. As there are some cases where if I put the sched deadline without trying these experiments without disabling the admission test, otherwise it wouldn't let me, basically, because I'm filling it basically to the brim, and probably there's some computer calculation that says no to my to the admission test. This was with m=1, so I'm just running with one core, and this was with 2 cores. No, not 2, 5. So I'm doing 6 tasks, and it's nice to see that the last task is the one that basically gets a bit unfortunate, that always keeps having to change a processor, basically. And again, with no interference, we have this runtime and period that is pretty good. But with the interference, we have something a little bit weirder, because then it tries to just accumulate periods all together. So it runs for multiple periods all at once. But it's still within the boundaries that we set before with the latency and alpha that we had to calculate theoretically.
What's the interference? Interference for what?
These ones, you mean? The first one is just running a single task for it's for control, basically. I'm just saying with this, with no interference from any other task, just a single task, how is it behaving? And what if I add workload to the CPU? How does it happen? Does it get worse? Does it get better? And I have these values. Again, Skedadder, we tried it a bit, still same thing. Of course, here the latency parameter is not really going to matter much because we don't have latency guarantees. And there's going to be some points in the graph that make sense after all, because we're due to how the slack is calculated, every time I cap the slack value, I'm not basically counting that as CPU time. Therefore, it's going to go negative because it thinks that it's not getting enough time. Because it's getting it before, but then is not giving me more in the latency I want. So with Skedadder, with m=1, we have this, again, spiky graph that slowly goes down, possibly because I set it, this is running with another task competing, so they're technically using 50% of the CPU each. And it's possibly losing a little bit of time, maybe due to sched switch, maybe due to random tasks that are still in the CPU. So it's nice to see that this allows me to see some trend lines that tell me how generally the task works. Because what I figured out is that the kernel shark view, while nice, doesn't really tell me at in a graphical way properly if the task is getting enough time or not. It's really difficult to see all the various bars, the activations, but I don't know if they are dense enough, basically. So this is a nice way to see, is it getting enough rate? Is it not? And of course, when it's capped, technically it's getting more. So this graph without that cap is going to be shifted a little bit. In these cases, towards the end of the tasks, I'm not getting as much as anymore. Maybe I'm hitting some penalty from the scheduler that says you're hogging the CPU. I'm not giving you more time. So it's also nice to see that at a glance that all of these things are easily noticeable. Again, M4 and M5, since these are single runs, it's a bit difficult to see a proper trend, a proper deal, because every run is different. So sometimes I'm getting more, sometimes I'm getting less. There's weird spikes, there's way more CPU that I'm given. So it's not as straightforward for me, especially in Skedadder. I still cannot properly tell how it behaves with just this metric.
Yeah, but I think that you can derive like the runtime and the period with the internal structures of the VDF, because it has that the idea of virtual deadlines as well. Even though we don't have in the user space as an information, we have it in the kernel. So it might be useful, not necessarily because on the deadline scheduler, we have something regular, so it's easy to do like a linear thinking and go to the infinity and beyond thinking of that. On the schedule fair, it might change because you can overload the CPU, so the values can go back and forth. But so it's hard for you to think if the task is making the deadline from the user space or from the user view. But you can use this mechanism to see if the scheduler is giving what it's supposed to give with the internal parameters. Even you might just shift it back and forth, so it's be fixed. But you can derive it from the workload.
If I were to just remove the latency cap, where the is giving a maximum value to the Slack, that would give the how much time that CPU has given me versus how much I've been slept. But the metric is also easily available by just summing the execution time versus the sleep time. That I think there are already two metrics that in the kernel do something very similar.
We can use this to check this scheduler itself. If the scheduler is doing what its parameters inside the kernel are supposed to do. More than the deadline for the user. It's
because as an eBPF, I'm just sending this as a program. I tell the alpha rate and the latency, and then it starts. It takes the first instant that it sees at out 0, so the first thing, and then no matter what, I'm thinking that the first time I see is the scheduling out, and then as soon as I get an event, if it's another scheduling out, then I know that I was in. The latency doesn't change because it means I was already at the maximum value. Instead, if it was an in event, it means I was out, and therefore I start removing Slack already.
Just one question. When you are drawing the line, let's put it this way, you guys are not thinking, you're thinking on eternal activation. It's a linear. It's not one activation on the other or the other or the other. It's a linear thing. That's perfect. That's why it would fit well with any scheduler. It's good.
And
I was expecting that from Bini. That's a cool thing.
Exactly. My questions here at the end is simply, now that I've said everything about what I did as a Slack, is like, is it useful? Does it work with anything? I'm not sure. I just had to take a problem. I tried to give a very efficient, hopefully, way to monitor it. I know that the eBPF version is probably going to be a lot less efficient for me because I'm doing the ring buffer to sending events, while in the kernel version, or maybe your version as well, for eBPF, I'm not even sending the events. So I'm just tracing and already doing the update in place.
No, this thing we can discuss and do experiments. That's the implementation part. That's,
yeah.
Let's say, academically speaking, that is the easiest part. But I think that the hardest part we already did. It doesn't work only for a scale deadline. If it works for a scale deadline as a user's perspective, because we have the parameters, so you know what to expect, right? To the sched order, we might change the view and not try to think if the user is getting what they want, but if the scheduler is actually behaving as it is expecting from the parameters that they have internally. And because it's a linear thing and you don't have like the activation as a parameter, it scales as I did.
Yeah, if I may comment briefly in complementing what Michele said, I think that first, sched deadline does not guarantee that the runtime is given with a deadline, because if you have high load, you will exceed the deadline. There is
No, that's no,
right. No, and no, then this may allow to check how you exceed that, and true. I mean, for I think you comment on that. I mean, the bandwidth for sched other, yes, true. Is I mean, I'm not so familiar with the code. I was just browsing now, and I think it is exactly what is it? The weight divided by LW dot weight. So I mean, like the weight of the task divided by the total weight that is everywhere. And of course, this is going to change when tasks is coming in and out. Of course,
it becomes dynamic, and then but you are more interested.
But I can change. Yes, but if I may like to do it, I may change. Maybe one day. I mean, right now I think the value of alpha is set in some way which I don't know. I don't remember. But nothing prevents us to change
that. Yeah, it's scaled. Because it's linear, it's scaled.
Yes, and I think to answer again, I mean, you made this comment already, right? So we don't rely on periodic releases. Yeah. It applies to any type of workload. Yeah. So
no, and that's why I was expecting that from you.
Yes,
and that's why you don't fall into the problems that we were discussing before on trying to figure out the runtime of the tasks, because you are linear.
It could be anything.
You don't care about when it ends.
I'm just checking the in and out times from a user point of view almost.
No, that's good. It generalizes. Perfect.
Oh.
You get it.
No, both.
That should be it. So thank you.
Good work.
Question?
Good work.
If there's a question, of course.
So just to try to better understand what you're doing, I wonder why this has to be done dynamically, and could you just use the output of trace command and then maybe play with different values of alpha or whatever?
Sorry, can you repeat the last part? I couldn't hear it very well.
Why does it have to be done dynamically?
Okay.
Well, can you just do the same thing based on a trace that's collected? Just the sched switch information? And then just record that and then compute whatever formulas you want?
Right. So it can be done offline, as in I can just check the trace afterwards, after the fact. But the entire point that this is actually nicer to do online is exactly, again, because of the, where is it? Is it the runtime verification system? Because what I'm doing here is at every point that I'm tracing, rather than sending the user immediately the value, I can already act upon it. This allows me to basically put a hook whether the Slack condition goes negative, and I could change the priority of the task I'm monitoring so that instead it gets the bandwidth I want.
Okay, yeah, that's kind of an orthogonal thing.
Does it make sense?
I can definitely understand that as a point of view, but The contradictory point of view is that you can only do the thing that you planned to do when you were running. So if you're not 100% sure of how you want your thing to be designed, then kind of an offline system could be better because you could experiment with different options.
At the end, these three things,
question.
there is a taxonomy on the runtime verification. It can be offline, online asynchronous, and online synchronous. So he's trying not asynchronous here, but the offline is just easier. It's easier to get back from, if you can do it at runtime, you can do it offline as well.
Okay.
And then you can simulate, offline is better to simulation. Yeah.
Okay, thank you.
And he even using the correct terminology. That I'm always speaking with terminology.
Yes.
The guy said,
we can work with that.
I was actually impressed by in the opposite direction. I really like that it was online because you can correct and take action. No,
you can do that. You can do both, but it makes it okay.
Offline, it's after the task is finished.
Okay, there are two things. He might correct the parameters online and offline. For example, if CFS, if they start changing the parameters that you use, you can do that online.
Yeah.
Yeah. You can do that online and offline, it doesn't matter. So the thing that the correct word is react. Online, he can react.
I like react.
Yeah. And in the current version in eBPF, we react after the fact. In kernel, it's easier to react during the fact. That online is synchronous.
Yeah. In the kernel version, I did put some file system hooks in order to change the alpha rate on the runtime.
Yeah.
Again, not a kernel developer, so it's probably not great.
That's why each monitor has a folder.
Yes.
You see that each monitor has a folder because in the folder we can put parameters. You did it right.
Yeah. Can you recall me how do you select the alpha at the beginning of?
Right. Alpha is selected by the user. Therefore, when you're already at, before even running the task or when it's running, you're telling that I want X% of the CPU. So I modeled it as X over Y. So it's just a ratio of from 0 to 1. Of course, the numerator cannot be 0 because therefore the lower bound function would just be flat and the slack value would be infinity, which does not really make sense.
Actually, I have another call. Can you, Michele, go please to the experiment when you have the line just below?
This one?
No, where you have this one here. I mean, something that I think here, I mean, I would like to convey is that, so in theory, since we have, I think, in this case, m equal to 1 and 2 tasks to together with same weight, you would expect them to have the same share, 50-50, easy, right? And so that's the value we set. We set alpha 1/2. So the slope that we see here is basically a representation of the amount of bandwidth that is consumed by the OS itself. So that's the deviation from the theoretical 1/2 and what it gets. If you guys want to, I mean, I guess you must have in the kernel somewhere the amount of bandwidth that is wasted in kernel decision. I mean, and if it's not, maybe that could be a way to account for it, because it's somewhere, I mean, the kernel decision costs, right? And how much do they cost? Well, we don't know before running because it depends on the machine, it depends on architecture, and how do you do? That could, maybe there are tons of ways, I don't know, you know better than me, but that could be one way, right? I don't know.
I think it's very insightful because I believe that when you need to write a scheduler algorithm, I think it's kind of tricky to estimate how much of overhead in the computation to schedule my task is too much, you know? Because if I spend a lot of time to save a little bit of time, it doesn't make any sense. But Yeah, and this shows you kind of like.
Because in theory here the plot should be flat. So the theory, because if you have you set alpha and you really get 50%, that would be flat. But it's slowly decaying, right? So the slack is decreasing, decreasing, and it will eventually touch zero at some point later.
And of course, in a single core, it works pretty well. With multiple cores, it goes a bit different because it's not exactly that predictable in these cases. As migrations happen, maybe there's a free CPU, maybe there's not. It kind of depends. I'm only checking one single task right now. In the kernel version, I don't know yet how to monitor multiple, mostly because it probably needs to be a hash map, a list, something. So I just took for the easiest implementation, I'll just have one. In the BPF version, instead, I'm using hash maps for with the process ID as a value, so I can eventually monitor multiple at the same time.
In the kernel version, we can use, we have a space on the task struct.
Probably.
Yeah, no, we already have, yeah. Yeah, we already have a pointer to avoid. So you can allocate any data per task and have it there.
From an outsider point of view, that I'm building it as a module or a program, I didn't want to touch any of the internals because
there's a space on the task structure for us to save per task monitor.
So I'm not sure about the feasibility at times because the alpha rate that I'm giving counts for every sleep, as in all the time that it hasn't been on the CPU. Maybe can be refined by only counting the time that it should have been on the CPU. I'm not sure. Maybe there's some discounts for IO waits. I don't know. But this counts for the latency anyway. So if it doesn't get enough time until this point, then I'm basically already failing.
But we are assuming on the computation of the linear thing, we are assuming periodic task, right?
No, I'm not assuming any type of task here.
But if you deviate, if you sleep for too long,
this will still go down basically.
Okay.
So that's a limitation that I have. So again, it could be that a sleep would maybe pause this, but then there's the point of, at that point, I'm not really following the linear lower bound anymore because I'm not getting the resource every latency second.
That's the point. Yeah, this works for the periodic, doesn't work for sporadic. Yeah, I need to check. I need to read, but I think.
Yeah.
But these are simple things. It's actually, because it's linear, it's easy to pick.
If there's anything else, I'm not sure. Otherwise.
Bravo, bravo.